Hey, welcome back, everyone. Good to have you here. We're going to be continuing on our series on video over TCP/IP. Last time we talked about the basics of what the wireless side, and this time we're going to really get into the nuts and bolts of Wi-Fi. So that's the area that we're going to cover. So let's get started. So the Wi-Fi protocol is Wi-Fi, by the way, for those of you who are interested. Wi-Fi actually doesn't mean anything. Some people think it's called wireless fidelity or something along that lines, and it's actually not. It is a registered trademark from the Wi-Fi Alliance, and it's basically a marketing term. It's designed to sell Wi-Fi. But it comes from a standard that is called the 802.11 protocol standard. And it's widely used. It's seemingly easy to set up. You know, where we see Wi-Fi all over the place. It's ubiquitous now. It's plug and play, right? You just turn it on and it works. Well, not really. If you are not really concerned about reliability or high bandwidth or low latency, yeah, it's plug and play. But if you really need those features, you need high reliability, high bandwidth, low latency, it's not nearly as easy as it sounds. And so that's what we're just going to be covering for the next little bit. Wi-Fi by design is designed to operate fairly well in an imperfect RF environment. It assumes that there's going to be interference, that there's going to be other access points, other stuff in the air, and so it's designed for that. However, with that design, it really requires a very high level of overhead, basically between 40 and 50% overhead. It has high latency sometimes and retransmission of data, and those, you know, high latency and retransmission, that is totally acceptable in Wi-Fi. If that's what it needs to do, it's perfectly fine doing that. Now that means that the data will still get through. And for the most part, if you're doing web browsing and you're doing, you know, internet access, it all works fairly well. If you are concerned about doing video with low latency and high transmission, those things are problematic. So some of the things that you need to know, there are some legacy products out there. So you've probably heard of them, 802.11, A, B, and G. Those are older legacy products. They're still out there, and you might have one of these access points in your home or your business, etc. Do not use these for NDI. They really don't have the bandwidth and the capability of making good use of NDI or HCX. Yes, 8HX may work on this, but not very reliably. So I would generally stay away from B, G, and A. The ones that you really want to focus on are 802.11n or AC. Now AC is obviously the newer one, and N is available in 2.4 and 5 gigahertz. AC is only available in 5 gigahertz. Okay, so there's no such thing as 2.4. 2.4 in 802.11 AC. Full NDI, so HX is great, very efficient, and so you can run it over wireless. If you're wanting to do full NDI, so for example, if you've got a bird dog device or maybe a camera or something, and you're trying to send that over Wi-Fi, you have to be extremely careful because again, you need that 70 to 100 meg of guaranteed throughput. Wi-Fi can go up and down and change gears, speeds, very, very quickly. And you really need to do careful management in a clean RF environment in order to make it work. And you have to use, obviously, N or AC. There's just no getting around that. Wi-Fi APs are not all the same. So marketing materials make it very difficult to figure out what you're buying, unfortunately. And even if you buy something, it's you know, one vendor, you would think that all Wi-Fi is Wi-Fi, but that is far from the truth. If you buy vendor A, B, and C, and you do exactly the same thing, on the box it might say that they are all that feature set, but they will all operate differently, and some of them are very poor. So if you're buying Wi-Fi off the shelf, Best Buy, all of the small stores, consumer products, be very, very careful. I would suggest that you buy some enterprise level access points. Obviously, those are more expensive, so a lot of you are going to be buying the less expensive stuff. But be very careful what you buy. Again, the adage is, you pay for what you get. So the other thing is Wi-Fi endpoints. In other words, your laptops, phones, etc. They also differ greatly. So if you have an Android device, if you have an iOS, a laptop, all of them have different chips in them, and so you'll get various performance depending on what kind of product you're going to be using. So you have to really know your stuff. So before we go any further, we're going to do a small little section here on some basics, and then we're going to end this particular section because it's going to be getting a little bit long-winded, and we're going to do another part. So let's take a look at these, and then we'll keep on going. So first of all, in Wi-Fi, there's something called modulation. And this is, I've got this written down here as Wi-Fi basics, but really modulation is, everything is, doesn't matter what kind of wireless you use. In fact, we modulate all the time. If you remember, for those of you who are old enough to remember dial-up days, when you hooked up a computer up to a modem, you would get that squawk, and it would dial, and then you'd hear this kind of this beeping, squawking sound, and then it would connect. Why was it called a modem? Well, a modem is modulation, demodulation. It takes digital data, converts it into voice sounds, and then at the other end it breaks it back down again. So we modulate in everything. It doesn't matter if you're doing Ethernet, if you're doing fiber, if you're doing anything. Basically we modulate. Well, what does that mean? Basically, radios will encode, in other words, take binary or digital data and convert it into something that can go over the air. So when you're sending some information, you can send a single piece of information, or you can send multiple pieces of information. So if you think about it, if I wanted to send one piece of information, I would send out one transmission. If I wanted to send out 10 pieces of information, I could send out 10 transmissions, or if I was able to, I could encode or else send all 10 pieces in a single transmission. So if that's what I do, then basically if I encode it, I increase the modulation, I stuff more data into a single transmission. So radios have lots of different levels of modulation. So you have low modulation, where very few pieces of information are sent, and then you have high modulation, where you stuff in lots of information. So what does that mean? It means that if you want to send large amounts of information, you have to have a better signal strength and a better quality of signal. If you have poor quality, then you're going to be sending less data, and so you obviously less speed. The further you are away from an AP, or if you have obstructions in the way, walls, something that is in the way, that means that you're going to have weaker signal. If you have other RF information out there, if you have other vendors, other access points, etc., you're not going to have as clean of signal, and therefore your quality is going to go down. And so that is going to degrade the quality of the link. If you have those combined, if you have a good solid signal and a good signal quality, your data rate goes up. If it decreases either one of those, then your speed is going to go down. So it automatically switches through these, and the radios will always make those decisions on the fly, and so they'll move up and down in terms of the speed. To give you an example, let's say you are connected in your office and you're downloading a file and you're getting really good speed. Then you walk with your laptop and you walk through to a couple offices down, and you're working there, but your speed has gone down significantly. Well, why is that? Well, it's because the RF signal is actually going through a number of walls. Glass, drywall, whatever else it goes down, which means that your signal strength is going to go down, and therefore you're going to be getting less speed. Okay, so that's just an example. The other thing is that channel size. So we typically refer to something called as 20 megahertz channels. That's just the width of our signal. In B, G, and N, or A, B, and G, we're limited to 20 megahertz channels. In N, we can do 20 or 40 megahertz channels. And in AC, now we can go 20, 40, 80, and 160 megahertz channels. So we can get really, really wide. Don't get too excited about the 80 and 160. The problem is you have to have an insanely good quality signal in order to use those. There's lots of opportunities for interference, etc. So most people do not actually use 80 or 160 unless you're in your home or something along that line. So mostly we only use 20 and 40 megahertz. Larger channels make for higher bandwidth. Again, not only are you stuffing more data, but now you're actually increasing the width of the data, so you can get more and more data in. Larger channels require better signal and better quality, is really what it comes down to. They are also more susceptible to interference, and so typically, again, we use 20 or 40 megahertz channels. In 2.4 we use 20, and in 5 gigahertz we often use 40. And then the final piece of the puzzle is that there is something called MIMO, multiple input, multiple output. So on a Wi-Fi system, you have well, if you look at one, quite often you'll see a bunch of antennas coming out of the top. Not all of them have that, but I think it's more of a marketing thing than anything else. But anyway, so basically multiple output, multiple input means that there are multiple transceivers, transmitters and receivers. So each transmitter or transceiver can send separate data. It's got its own antenna. So for example, 802.11n had up to 3 transceivers, so 3 antennas. AC now has up to 4, and in theory it could go up to 8. That's what the standard calls for, but nobody has ever made anything beyond 4 so far. So each antenna can receive and transmit different data. So if you had 2 antennas, you could double the amount of data that you're sending. If you had 3 antennas, you could triple the amount. However, it's always limited to the least common denominator. So if you had a 4 by 4 access point, so in other words 4 antennas, but you were connected with your phone, which is a 2 antenna system quite often, then you're only going to be transmitting at 2. You can't use 4 because you don't have the end device is only 2. So just keep that in mind. You can buy the latest, greatest 4 antenna system, but if all of your devices out there are 2 antenna endpoints, then you're never going to talk 4 by 4. You're only going to talk 2 by 2. So the other part is, how does Wi-Fi actually work? So Wi-Fi actually is, like I said, is not a very efficient protocol. It's designed for high interference, high noisy environments. So it uses something called collision detection carrier sense multiple access collision avoidance, CDMA-CA. The process with this is that in Wi-Fi, only one device can talk at a time. In AC Wave 2, there's some new changes that allow multiple devices to talk, but that's still in its infancy, and it only works some of the time with certain devices, so it's still a ways to go on that one. But basically, before any device can talk, it can't just start talking. And the reason for that is because you're not actually physically connected. So going back to last session, we talked about Ethernet. Well, we're actually plugged into a switch. We can tell if somebody else is talking. We know exactly who's talking, when they're talking, how long they're talking, everything else. In wireless, we don't have that opportunity because we're not physically connected. So devices basically have to, first of all, listen. They kind of open their ears in wireless and they say, hey, is anybody out there? Anybody talking? So they must listen first. If there's somebody else talking, they back off. So they basically say, okay, somebody's talking. I'll try to figure out how long they're talking for by reading information from the packet. I'll back off that amount. And then after that back off time, I'll add a little bit of extra time. It's actually a random time, and then I'll try it again. And I just keep on trying, keep on trying, keep on trying until I can talk. If there's nobody else talking, you would think that you would start talking right away, but that's not actually true. You pause first for a random amount of time, then you check again, and if it's still clear, then you can start sending. If it's not clear, then you have to start the whole process all over again. So that's why Wi-Fi is so process inefficient, in that it does all of this extra stuff in order to avoid communication issues. The other thing is if a collision does occur, in other words, when two devices do talk for whatever reason, they basically all wait for an acknowledgement. They say, hey, I just sent something, and the end device sends back a message saying, yep, I got it. If they don't get that acknowledgement, then they restart retransmitting that data. And that happens in Wi-Fi all the time. That's just part of the protocol. The more collisions, the more retransmission that happens, the slower things get. So if you have a very noisy environment, that's one of the reasons why you don't get as much throughput. So if you take a look at some of the speeds, and again, these are the theoretical speeds, these aren't the actual speeds, but if you were to take a look at 802.11n, and if you were running at the highest speed 20 megahertz channel with a single antenna, you would get about 72 meg. If you were to go to a 40 megahertz channel, then you're up to about 150 meg. Now those numbers seem really great. However, right off the top, you have to take off about 40% off the top. So 72, you're getting about 43, 42 meg of actual throughput. 150, you're down to in the 90s. So that's part of the marketing problem, is that when you look at the box on Wi-Fi, they'll always throw these big numbers at you. They'll say this is 150 meg, 300 meg, 600 meg. Always remember to divide that by, or take off at least 40% off the top for overhead. So if I went to 2 streams, then I'm up to 300 meg, again, 40% off. And if I went to 3 streams, then I'm at 450 meg. Okay, so those are the maximum capabilities. If I went to AC, if I went to a single stream, I could get, for example, 200 meg. If I went to an 80 megahertz wide channel, I could get 430 meg. But again, 80 megahertz channel is almost impossible to get. So that's why, again, from a marketing standpoint, you see these big numbers, but they don't necessarily mean much. And if you really wanted to go crazy, you could go all the way up to 80 megahertz channel with 3 streams, for example, and get 1.3 gig, which is pretty much impossible. But just that's what's written down. So the final part about RF is you really have to understand your RF environment. So this is a screenshot of what I took a shot of in my office. This is what is called a Wi-Fi Wi-Fi scan, and you'll see that there's lots of information in here. It shows me my 2.4, my 5 gigahertz, and we'll expand this a little bit here. But this is all of you should have these things on your laptops or on your phones or your tablets, because when you go into an environment, you want to be able to check to see what's going on in Wi-Fi. So how do you actually interpret this? So this is the 2.4 range, this is the 5 gigahertz. I'm using a product called Insider, but there's lots of other ones out there. There's lots of good ones, so whatever fits your budget. So let's take a look at what this would look like if I went into a 2.4. So this is the 2.4 here. You'll notice down at the bottom, first of all, it tells me my channels. Now, in North America, we have up to 11 channels. But each one of those channels is only 5 megahertz wide. Now, I already said that generally we use 20 or 40 megahertz channels. So if you were, for example, to use channel 3, you're actually using all the way from 1 all the way up to 6, essentially. And if you're using channel 1, you're using well below 1 all the way up to 3. So it's 20 megahertz wide, those numbers are only 5 wide. So in 2.4, you really only have 3 channels available to use. And most of the time we use 1, 6, and 11 because those are the ones that don't overlap. Anytime we have overlapping channels, you have potential interference. And you can see right here in this environment, in my environment here, I've got a lot of stuff happening. There's lots of access points, there's lots of things going on. On the side, you'll see a bunch of numbers, and this refers to as the signal strength. So you'll see that I've got neg 30 all the way to neg 90. The numbers basically, the way RF is that the measurement is always in negative numbers. So if I were to have a neg 40, that is a fantastic, good, super strong signal. If I were to have a neg 80 or neg 90, that's a weak signal. And it doesn't go all the way up to 100, it actually goes beyond that. So you could have, not in Wi-Fi, but in some other devices, it might be even 105, 110 signal strength, and that's perfectly fine. So if I were to use an example here and I went to, let's say I'm connecting on this RRT guest system right here. Well, RRT guest is connected at neg 47. The next access point that I'm concerned about is this one called SHA-2F9. The one in the middle there, the RRT solo, I happen to know that it's on my same system, and so I can ignore that, but that's my own thing. But you'll notice that the SHA one is at neg 67. So that gives me a difference between my signal and the next noisiest signal is what is called 20 dB, or my signal to noise ratio is 20 dB. Okay, so keep that in mind. My signal strength is 47, my SNR is 20. Okay, so if I were to look at this, if I was running 802.11n, I would basically operate down in this section here. I would be operating at I'd be operating at about 100 and in 20 megahertz channel about 65 meg, and 40 megahertz about 135, and again minus 40% off the top. Now why? Well, because I'm getting neg 47, which is fantastic. So why am I not running at the highest level, which is 150 meg? Well, the reason is that my signal to noise is not good enough. I have a 20 dB fade margin. I would need 25 SNR in order to, sorry, not fade margin, but my SNR, I would need a 25 in order to run at the highest modulation. Now, let's say things deteriorate. I get some noise, I get, maybe I move to another area, or something else happens. Well, it's very, very common to all of a sudden move down into a weaker signal, right? So all of a sudden now I'm down into the 30 megahertz range, for example, or 30 meg. And then, signal gets better, and then I move back up to 90 meg. This happens automatically in the system. This is the way Wi-Fi works. It goes up and down through these different modulations. Now, I'm only showing you a single stream. What happens if I go to 2 streams? Okay, so if I go to 2 streams, I would start off at this one, and I would move back to, if the signal deteriorated, I might go down to this one. Just because you have a 2-stream system does not mean that you're always going to be operating in 2 streams. You might not have, you might be behind some walls, some reflected signal, etc. And the system says, no, you've got a 2-stream system, but it's not good enough to run in 2-stream. I need to be running in signal stream. And the radios will automatically move between all of these systems. Okay? So that's how Wi-Fi works. Now, also in 5 gigahertz, you'll notice that this is what my 5 gigahertz looks like. I've still got a lot of information, or a lot of access points in here, but you'll also notice that there's something strange here. You'll see the channel sizes, but then you'll also see this big blank area over here, and you go, well, wow, why don't I use those channels? Well, you can, absolutely, and you should. However, you got to also realize that there is some rules that these center channels, 5.2 and 5.4, use, and they follow something called DFS rules. DFS rules means that you're constantly listening, and if you get a signal, you have to turn off for 1 minute, and you have to lock that channel and not use it for half an hour. It's just part of a regulation. It's a regulation used widely all over the world, and you have to follow it. So a lot of people don't use these channels for that particular reason. If you are near an airport, or if you're near a Doppler radar, one of those towers with those big snowballs on the top, you will get DFS triggers all the time, and you will not be able to use 5.2 or 5.4. It'll just be a mess for you. But if you are not near that, and if you don't have issues with DFS, by all means, you can use those channels, and those are actually really clean because a lot of people don't use them. So, lastly, in an RF environment, it's easy to think that we're just are concerned about Wi-Fi, but that's not true. We need to also understand that there's lots of other things going on. This is what is called a spectrum scan, and a spectrum scan basically shows you what's going on in your RF environment besides the Wi-Fi. It includes Wi-Fi, but it shows you everything else. And particularly in 2.4, there's lots of other things in 2.4. For example, Bluetooth, baby monitors, audio systems, wireless audio systems, surveillance cameras, microwave ovens, for example, is in 2.4. So quite often you need to also invest in maybe a spectrum scanner so that you know exactly what's going on, not just Wi-Fi. So the Wi-Fi scanners are easy to get. They're very cheap, either free or next to free. Scanners, spectrum scanners, not so much. Spectrum scanner would set you back probably $1,000. But it is really very handy to know what's going on in your environment. So this really helps you to decide what's going on and what you can use. Okay, so some of the challenges. RF is a hostile environment. It's designed for an imperfect RF environments. There is no single environment the same. So if you are in your office today and you move to a different office, the conditions are going to be completely different. If you go to an arena, for example, it will change. And also be aware that RF conditions change by the hour. So for example, if you go to an arena and there's nobody there, you're going to have one set of RF conditions. As soon as everybody starts piling in, they're going to bring their cell phones, they're going to bring video cameras, they're going to bring all kinds of other stuff. Your RF conditions will change drastically between the time that when there's nobody there and then when there's somebody there. So you really need to check all the time. Without careful analysis and planning, Wi-Fi can be very unpredictable and problematic. So you might say, by now you might say, well, why in the world am I using Wi-Fi? Why even bother? Well, it's very easy to use, it's widely used, and if you know what you're doing and if you plan properly, it can be used effectively, but you really, really, really need to understand it and plan for it. All right, we're going to wrap up this particular session. We've been covering a lot of information on Wi-Fi. For some of you, this has been a little bit heavy. There's a lot more information, or there's lots of information in here, but hopefully this will give you kind of a look behind the curtain of what's going on Wi-Fi, and that will help you kind of doing some troubleshooting, setup, determining what is necessary in order for Wi-Fi to work properly, and to also give you an idea of how to troubleshoot. It's of course not exhaustive by any means, but it should give you some pointers in the right direction. So some of the things that we covered modulation, just the way that the radios move up and down through different levels of modulation, increasing and decreasing the amount of throughput that is available, and that is very dependent on signal strength, SNR, your signal to noise ratio. And we took a look at some of the things that determine modulation. We also looked at channel size, 20, 40, 80, even 160 megahertz channels, and the pluses and minuses for those. And the understanding that in a typical environment, you'd be running in 20 and 40 megahertz channels. 6 or 80 is wonderful, and 160 is really huge. But you probably will not be able to use those in a production type of environment. We also looked at MIMO spatial streams. the ability for multiple transceivers with multiple antennas. So the more transceivers you have, the more throughput that you can actually get through on a particular wireless system. Again, there is pros and cons for that, and it depends on what kind of equipment you have, but that gives you some ideas of how that works. Then we looked at CDMA/CA, and that's really kind of how Wi-Fi works and why there's some of the overhead. Again, Wi-Fi was really designed for a imperfect RF environment, and so there's a lot of overhead. If you don't do things right, if you don't plan for it well, you can get yourself into real trouble. On the other hand, it can actually be a really good use of technology for what you're trying to do. So give you an idea of how that worked. Then we also looked at some of the tools, basically your Wi-Fi analysis and your spectrum analysis, to give you an idea of what's actually in your environment. So that's kind of the end of today. For the next time, we are actually going to kind of put everything all together. We're going to take a look at how do you, what do you look for when you're purchasing an access point? What is a good access point? What is a poor access point? How do you make sure that when you place it, you put it into a location that is suitable for your equipment? How to make sure, you know, how far can you go, how close do you need to be in order to get the highest modulation that you need for the throughput, and how to also kind of make sure that everything is running properly, how to monitor it, and also make corrections if need be. So that's kind of where we're going. And then the final part of that, we're also going to be taking a look at other wireless technologies. Wi-Fi is certainly the most popular, but it's not the only method. In fact, there are other protocols that are actually more efficient, have higher throughput, etc., lower latency, but they are more proprietary type products, but can be very useful for what you're trying to accomplish. So we'll take a look at some of those as well. So thanks again for watching, and we will pick it up again next time. So let's go over to our final shot here, and we'll talk to you next time. Thank you very much.